Hello guys, so today we are here to solve this problem called find if path exists in a graph. So if a graph is connected, as we all know, that if a graph is connected, that between any two pair of vertices, there is a path. This path could be, it could consist of only a single edge or it could consist of multiple edges. But if one starts from one vertex, then he is always able to reach another vertex if the graph is connected. And this is true for all the vertices, all pair of vertices. So in a sense, we can say that if a graph is connected, then all the, vertices are mutually reachable from each other. Perfect. Now with this, what we will do, that we will try to solve this problem. Okay, so let's go ahead and go through this problem. There is a bidirectional graph. So it means that an edge can be directed from either, in either direction. So it could be from 0 to 1 and 1 to 0. Let's say, 0 is one vertex and 1 is another vertex, and there is an edge between 0 and 1 vertices. Then bidirectional means it can be, traversed from 0 to 1 and 1 to 0 in both ways. Okay, and each vertex is labeled 0, 2, and -1. The edges in the graph are represented as 2D integer array edges. So edges is a 2D integer array. Okay, and each edge tells whether the two vertices, each edge is an array having two vertices, and it tells whether these two vertices are connected mutually or not. So wherever two vertices are mutually connected, then that two component array is part of this edges two-dimensional array, and it shows this two vertices, vertex 1 and vertex 2, which are mutually connected by an edge. So an edge array vertex v1 comma vertex v2 will be there in part as a component of this two-dimensional edges array. With this understanding, we have to figure out if there exists a path between source vertex and destination vertex. Okay, so we have to return true if the path is there in between source vertex and destination vertex, if there is a valid path from source to destination. Otherwise you have to return false. Now see what we can do here, that if 0 and 1 are connected, then 0 and 1 are part of the same component. If 0 and 2 are connected, then 0 and 2 are part of the same component. If 0 and 2 is connected, then from 2 you can reach 1 also. So it means that if any number of vertices are connected and if they are part of the same component, then there is a path in between all these vertices. So what we are going to do, that we are trying to establish disjoint sets. For each component, there will be one disjoint set. Okay. And how are we going to do this disjoint set? So to do that disjoint set, what we will do that, first of all, let me change the layout. Okay. So to do that disjoint set, what we will do, that first of all, we will create one array of parent. Okay. And array parent. Okay, so what we'll do, that we'll take one element of the array, one element of the this graph as, okay, so this is there, and then we will start this array, this parent array, with the value parent array -1. Okay, now with this, what we'll do, that uh we will take for each edge, for int array edges, edge, not edges. Edges is the incoming two-dimensional array. So we are separating it. Now we'll do, what we'll do, that we'll find one, what we'll do, that, for every component of the graph, we'll be taking one representative element. Okay. And that representative element will be found out by using this function parent, and we'll be passing this edge, 0th element. And here only we can do correct. JK is equal to find parent edge 1, like this. What we will do, Okay, now we will check if j is not equal to k. So j is not equal to k, it means that the zeroth edge and zeroth component of the edge, I mean to say zeroth vertex of the edge array is different from, is in different component than the first vertex of the edge component. If it is like that, if it is like that, then obviously we have to make them, point to the, parent of k is equal to j. Like that we have to do. Okay. So if we are doing this, then obviously our work is done. Okay. And this for loop is done. And then what we will do, that we will, do for int source set is equal to of find of find of the parent array will pass the source here. So this will be the which component this source belongs to, and what is the component of the destination vertex. If source set is equal to destination set, return true, else return false. And what we will do, that private int find of int array parent and int any vertex, I is any vertex. So what we'll do that, if parent of ith vertex value is containing -1, then obviously I is its own, root, it's in that same root. Okay, otherwise what we'll do, that we'll do again call, find, we'll pass this parent array, and then so now parent of I is not -1. So parent of I is some other, uh, vertex. So on that vertex again we'll call that parent of, we'll do find. On calling that find, we will be able to go to that index of that array and check whether it is -1 or not. So we'll keep on doing this. This is a recursive call. We will keep on doing this unless and until we hit this, if parent of I is equal to -1. And once we hit that parent of I is equal to -1, what we are going to do, that, we will be, at in each index location, we will be, putting this returned value, so that, the every different vertex is connected by just a single edge with the root vertex. If this is the case, then after accomplishing this, what we will do, that we will be returning parent of I. Okay, like this. Okay, okay, okay. And then what we will do, that, we will run this. So it's saying wrong. Cannot find symbol dest set. Yeah. Dest set. We'll run this. Perfect. Perfect. So again, I would like to go through this, solution. What we are trying to achieve in this, that, we are imagining this, solution in terms of connectedness of the graph. If a graph is connected, then between any two, arbitrary vertices of that graph, there will be a path. If that path is there, then we can access from one vertex to the other vertex through a single edge or a multiple edges path. Okay, with this, what we will do, that we will try to find, we will try to, figure out how many connected components are there in this graph. So to figure out what we will do, that, we will create a parent array. And in that parent array, we will mention that, okay, we will take one node as the representative element of that component of the graph, and all the other vertices which are connected to that will be pointing to that node. I mean to say, they'll be storing the index of that node. So, and accordingly, we have written this find. If find, so the node which is the representative, it will be having the value -1. Other nodes will be pointing to that node. Okay, so to figure out whether a node is root or not, we'll just check if parent of I is equal to, I mean to say, in that parent array, the ith index value is -1 or not. If it is, then I is the root, and we'll return the root. Otherwise, what we'll do, that we will, go to the find of parent of I. So parent of I will be storing some node, will be again going to that particular index, and again checking if parent of I is equal to -1. No, then again we'll be going to that content of that node, and in that way we'll be recursively calling that, and every call will be storing that value. Every call, we will be, storing that value. um, um, every call will, keep on happening unless and until we hit the root node. The root node will be storing -1. So as soon as we hit the -1, the recursion will stop, and that value will now be updated in all the nodes from where the call was happening. So all the nodes will be storing that index where the -1 value is stored, and that -1 value will be, in this way, it will be just one edge, at a distance of one edge from that root node. And this is the basic logic of collapsing find. And after updating that parent of I into all the nodes which are connected with the root node, we'll be returning that parent of I value. And that's it. This is what will be, giving us back the root element of that component. And so first of all, in between these lines from 5 to 10, we are establishing that, okay, if all the edges which are given in the incoming two-dimensional array, incoming, two-dimensional array, for all of them, we are creating a, set of connected components. And at the end, for the source vertex and the destination vertex, we are only checking whether the source vertex and destination vertex representative element are the same or not. For the connected component containing the source vertex, its representative element, and the representative element of the destination vertex, if they are same, then it means that both of them are in the same set. And if they are in the same set, then obviously it means that there is a path in between the two vertices. And if there is a path in between those two vertices, we are returning true, because that's what the problem says, that, if there is a path, we have to return true. Otherwise, if it is not, if there is no path, we are returning false. And that's how we are solving this problem. So again, I'll run this, and we will see that it's accepting, and we'll submit it. So it's solving many of the problems. So it's a good solution. It's still, it could be improved, but that will be, calling for other techniques and methods. Meanwhile, we'll be, if you have any doubt, please post it in the comments, and I'll happily try to answer those doubts. With this, I'm coming to an end of this video. Thanks a lot.